I'm going to talk about machine learning in complex systems, and most of this research is based on my doctoral thesis that I have defended recently in September here at ETH. And so, yeah, let's just dive straight into it. Let us start with this bit of like a grounding experience. So we're all on Earth, all in Switzerland, all in Zurich. And I want to point your attention to this one particular place, this little intersection here by the Limmat. And do you recognize it? Yeah, probably. Yeah. Have you ever like gone over it, walking, cycling? Anybody drove over this intersection? One person driving? Okay. It's good intersection. Like, what do you think? Okay, hard to say, right? Okay, so we're gonna be focusing on traffic. So we're kind of interested in intersections as this unit of traffic system, right, in the city. And so let us first formalize it a bit so that we can then kind of talk about it and get a feeling for when it's good, when it's bad. So first step in formalizing it, of course, we have intersections, just two roads meeting, and we're gonna have these incoming lanes and outgoing lanes. So the incoming ones here in red, they're gonna bring traffic to the intersection, and the blue ones, they're gonna kind of take the traffic out. And then if we take two of these, so one incoming lane and outgoing lane, that composes a movement, what's referred usually in the literature as a movement, and that is basically the path a vehicle would take over the intersection to cross it. And then these movements, the collection of these movements forms a phase. So these are the movements that can be actuated at the same time. And so not all movements can form a phase because generally we don't want these movements which are conflicting to be in one phase, right? And what is the conflicting movement? Basically, if a path of one movement would cross the path of the other, so the vehicles would cross at any point, that is a conflict. So generally when we're dealing with signal control and we want to give green to certain movements, we would only give green to movements which are not conflicting. And so we have this concept of conflicting movement. We can also extend that to phases, right? So we can have conflicting phases, and two phases conflict when any of the movements of given two phases would cross. And so here, visualized two phases which are conflicting because we cannot actuate them at the same time. That could lead to accidents, generally considered dangerous. Right. So now we want to control traffic over this intersection, right? Not everybody can go at the same time. And simple solution, in that case, let's say we only have these two phases that we shown in the previous slide. And a simple solution would just be to alternate them, right? Like give 30 seconds to the first one and then 30 seconds to the other one. This kind of works, but it has serious limitations because, of course, different times of day, maybe there's more people going along the Limmat than across. And so, we're giving 30 seconds and then no one is going and people are waiting. It doesn't make much sense. So a better solution would be to actually adapt to traffic conditions. And we can do that quite well. So what we need first, we need to get the data, real-time data from the intersection. It's kind of more, I guess now we could say traditional method would be what I'm kind of visualizing here, these inductive loops that we can put at the exit of the intersection and the entrance, and then we can count cars. So each time a vehicle passes over such an inductive loop, it's counted. And so we know how many vehicles entered and how many vehicles exited. We also have the time, so we can kind of derive from these numbers, rates of arrivals, rates of departures, all kinds of useful metrics. I think nowadays there's also kind of this new research that's looking into a bit, even more precise control with like maybe tracking cars with cameras, or you could also consider tracking people's mobile phones, but this of course carries very serious privacy issues. But some countries are probably considering that. Okay, so now we're going to adapt to traffic. That's great. We're going to have a better traffic at a single intersection, but the city is not only just one intersection, right? Like in Zurich, we have quite a lot of intersections, and what we have to think about is how does what we do at this one single intersection by the Limmat affects the whole traffic system. And so generally, we can have two sorts of interactions between intersections, I would say positive ones and negative ones, right? So there can be something happening in one intersection that affects the other in a positive way or a negative way. So here we see a positive example, so-called green waves. So basically a platoon of vehicles on an artery is given green consistently across several intersections. And that's, of course, very nice. Fluent traffic, people don't have to stop, good for the environment, quite a nice thing. The opposite of that would be a traffic jam. It's not, I don't know, not much to explain here. I think everybody kind of gets what a traffic jam is. Everybody hates it usually. Quite bad for everybody, also for the environment. So this is something we generally want to avoid. So basically, now we want some sort of traffic control system that allows us to control traffic at single intersections in a way that is good for these intersections, but then also somehow considers these interactions. And what we want is to promote the positive ones, for example, green waves. And so let me now give some examples of existing methods that kind of attempt to do this. So one such method is quite old already, from 2005, self-organizing traffic lights. And it's a decentralized system. So you only control traffic at single individual intersections without explicit kind of accounting for all of them. But the rules which are followed by these single intersections are designed in a way that is supposed to promote this sort of green wave effect at a systemic level. And then another method, slightly newer in analytic control, is based on, again, completely decentralized. We give sort of rules to individual intersections. And then by following these rules, there's an emergence of positive interactions between these intersections. And here we have this sort of optimization rule, which tries to, well, basically make the situation good at a single intersection, but then also kind of considering implicitly the neighbors, and the stabilization rule that makes sure there's no overflows, so that we don't create queues so long that they spill over to the neighbors. That's like generally the worst thing that can happen. And the interesting thing about this method is that it has been, and that doesn't happen that often for like traffic science, it has been recently tested in real life in a pilot study performed by a different group at ETH in 2020 here in Switzerland, in Lucerne. And they actually found that this method outperformed the other adaptive method that they've been using for quite some time in Lucerne quite significantly. And so this is one of the methods that we're gonna come back to. We're gonna refer back to it when I'm showing you some results. And then the third kind of approach, and this is a whole different sort of methodology, is using machine learning. And as you might expect, in recent years, it has become increasingly popular to apply machine learning to, well, anything really, and traffic is no different. So there has been quite a lot of papers applying machine learning methods, and this is usually done with reinforcement learning. I think the first publication was actually in around 2000s, and it's like a simple reinforcement learning method, tabular learning, I think. But nowadays we're moving towards like deep learning solutions, but still reinforcement learning. So the way generally it works for anyone who's not experienced with reinforcement learning, we get the data from the intersection, right? We call it this in terms of reinforcement learning, it would be called the state. And then we feed it into the neural network. And the goal of this neural network is to estimate the reward. So we have some notion of a reward, some notion of what is good, what we want at the intersection, and it estimates a reward for each action. The actions usually are the phases to be actuated. And then we choose the phase with the highest estimated expected reward. And so how does this model, this neural network, knows what a good thing is? Well, we have to train it. So we let it interact with the environment, and this is usually done in a simulation, like we cannot let it interact, with the world out there. That would be quite problematic, but so we have a simulation, we train it in the simulation, repeated interactions with the environment, and then it sort of, by trial and error, figures out what the right thing is and what the reward is going to be. And then in the beginning, when we train, this model really does not have any kind of insight into what the right thing is. And so we have to let it explore a bit so that it doesn't kind of fall into these local optimas. And so usually with some probability, and at first we take a random action to let it explore the space, and this probability decreases over time. Okay, so now I think we have a bit of a formalized intersection. We should get an idea of what we're trying to do here. I told you about some methods, some existing methods, and so that brings us to the first question that I was asking. And what I noticed, especially looking at these machine learning papers, and that was quite surprising, is that they never compared to existing methodologies. So you would have a paper, it would propose some machine learning method, they tend to be quite complex, and then it would just compare to other machine learning methods. And it would be like, okay, we're better than, 5% better than this like method from last year. but they never compared to existing methods. So I wanted to see how good these machine learning approaches really are when we compare them to what we already have, sort of like the state of the art. And then the second question is, how can we improve them? So like, regardless of whether they're performing good or bad with respect to these already existing solutions, we can always improve. And I think in traffic, it's often easy to kind of assume, okay, we just want to have a more fluent traffic. We want to have like lower average travel times, maybe bigger throughputs, so sort of performance metrics. But actually, there's quite a lot like other things we should consider. So of course, nowadays we're trying to really take into account notions of sustainability, and in traffic, that's quite a present problem. And there's also issues of adaptability, but then oversight as well. And so I'll try to kind of go over all these areas and how we can improve in them. But let us start with the first question. So let's see what happens if we compare an existing machine learning method to an existing adaptive method. And just like for starters, methods I'm going to use here is I already mentioned, we use simulations. And in particular, we're going to use CityFlow. It's a simulator that has been designed kind of specifically to deal with reinforcement learning methodologies. And we're going to focus on one particular simulated scenario that is inspired by Manhattan in New York. So this kind of grid-like network. Okay, so here on this New York scenario, we're comparing Presslight. So that's the machine learning method, deep reinforcement learning method. We compare it to the analytic algorithm that I've also mentioned using just the optimization rule. So I mentioned it has two rules, optimization and stabilization. For now, we're just comparing it to the optimization, to the algorithm using just the optimization rule. And we see Presslight is actually, the result is in terms of throughput. So the number of cars that goes through the system, and usually the intuition is like the more the better. And Presslight is not really doing that great. So this is training. So we start is of course not great, right? And then it improves. So we can see it's learning, it's getting better, but it's struggling to really reach comparable results to the analytic. And so I think immediately the second question, how can we improve it, comes to mind. So we want to see if there's some kind of inherent problem of machine learning not being able to deal with this complexity, or maybe if we kind of play around with the design, we can get better. And so we come back to this exploration phase, right? So we said that the algorithm, when it's training, will take some random actions to kind of get an idea of the situation, of what it needs to do. But we actually have a lot of insight into traffic and how it works. So perhaps we can speed up this exploration. We can kind of guide it into the areas of the search space that we know are kind of relevant. And so we propose this instead of epsilon greedy exploration, which is the kind of classical type of exploration where with some probability epsilon that we decrease over time, we do a random thing. We propose to do with, again, a decreasing probability, something that is recommended by the analytic algorithm. So kind of let this analytic algorithm that we know works well guide our exploration. And what does it do? So now the blue line is the algorithm, and it's kind of the same as Presslight, except for this exploration thing. And we can see two things. So now we're able to outperform the optimization rule of the analytic algorithm. We're able to get better, but also convergence is much faster. So we reach a good result much faster than Presslight would. And this has some consequences for not only for performance itself, but also for sustainability, because these models are actually kind of costly to train, right? Like we need computational power to train them. And this is also something we should consider, because in traffic, we might need to retrain quite often when the situation changes. And if we can kind of provide an algorithm that needs less training, trains faster, we use less computational power. So this also has positive effects for sustainability. All right, so we have an algorithm that works kind of like decently. And now we want to ask how adaptable really machine learning is. And we know machine learning can be quite brittle. And so when like things change, we expect it might be a challenge. So the first thing we want to see is how it adapts to non-homogeneous road network topologies. So we've been dealing with this kind of New York scenario, but it's a very particular network. I think in the States, it's quite representative, actually. The cities are quite grid-like oftentimes. If we compare it to Zurich, I mean, that's no grid. It's like completely different. Streets have different lengths. Some of them are one-way only. So it's a very different situation. And we would like to really propose something that will work in any city and not just in, very specific cases in the United States, right? And so what we propose is to change the state design of these machine learning algorithms. So the Presslight approach, as its state, would use the number of vehicles on each approach. So we would have these inductive loops. We would see, like, as cars go in, we would count them up, and we would tell the algorithm, okay, this is number of cars on this lane, this is number of cars on that lane. But this sort of forgets about the fact that lanes can have varying lengths, right? So we propose this length invariant state design, which implicitly has this information, carries that information for the algorithm. So we use occupancy. This is still the number of vehicles in a given lane, but proportional is the percentage of the road that these vehicles actually cover. And this could work fairly well with just assuming a vehicle is of a given length, because in the city, most vehicles will be, at least in most cities, it will be similar. Right, and then another thing that we propose is this kind of pre-training concept. So usually, and that's what we did for the previous results, we would train the algorithm on a given scenario and then deploy it also on that scenario, which already that could ring some bells. I mean, maybe it's a bit like cheating, right? Like we're training it on the same thing, then deploying it on the same thing, and it works, and kind of no surprise. So we want to see also what happens if we train it on this simpler scenario, grid-like scenario, and then deploy it to a bit more varied road network to see how it adapts. Okay, and then so what we see here, Presslight again does not perform so great. Analytic is better. So here actually we have average travel time. We're switching from throughput. These are kind of correlated, but now we want lower values, right? Lower travel times are better. People spend less time in traffic. That's good. So analytic again beats this kind of basic machine learning approach. And then we have guided light with our invariant state design, and that's better than analytic. And then we see that if we pre-train on a simpler scenario, we can actually get even better. So we see this method with the state design, it has quite a strong generalization ability. So being trained on a simpler scenario, we can actually extend to more complex ones. And then following up on that, so we asked about this adaptability to changing topologies, but usually street lengths don't necessarily change in real time. But there are a lot of things that happen in real time in traffic. And traffic can get very disrupted. So, accidents, roadworks, the network is kind of full of them. And accidents we really cannot predict, right? This is not something like a machine learning model can predict whether there's going to be an accident. We could have a statistical model that would say, okay, there's like this many accidents every year, but they're not going to tell us where exactly they're going to happen. So we kind of cannot, train for that. We cannot really include that in the training data. And so what we will do, we'll use this network, again, New York, and we will take out, as this sort of disruption, we'll take out some links and reroute traffic along them, around them. So, in a sense, we'll say, okay, there was an accident or there was a road work and the traffic has to go around this road is no longer available. And so what we see here, actually, is that machine learning, and this is, again, average travel time, also the analytic, we have few disruptions in the beginning and many disruptions at the far end. At first, it's like not even getting that much worse. It's variance is increasing a bit. And then it gets, progressively harder to control, because as we have many disruptions, the capacity of the network just decreases. We have fewer roads, we can put fewer cars in. But machine learning doesn't seem to learn at all, right? Like it's constantly bad. It's really bad in this case. So it's actually not able to learn in that scenario, which is quite interesting. It's mostly because this scenario is actually quite a difficult one. So as you see here, it's like these three arteries, and then you have traffic lights here, you have traffic lights here, so you have these also very short links between, and it's very easy for traffic to overflow in that setting. So basically, what happens when in training, we deploy the algorithm. At first it explores, even analytically. But of course, in the beginning, it's not going to be great. So it's going to make some mistakes, and congestion happens very quickly. And once congestion happens, the algorithm deals with a situation where no matter what it does, it's bad. Because basically, once you have an onset of congestion, usually no traffic policy can help. You just have to kind of wait it out. But so this is not a meaningful learning signal for this method. And then that kind of leads us to this idea that we had previously with pre-training, right? So we have this difficult scenario where the machine learning cannot really be trained properly, but we can deploy it to a simpler scenario and then just train it on that. And then after it's trained, put it to work on this more difficult one. And then we can see it actually improves significantly. And now we're able to reach kind of comparable performance to the analytic one. So the pre-training can not only improve this sort of adaptability, but also resilience in real time to changing conditions. All right, and then, so this is the final kind of project idea that was part of my thesis. And so we mentioned the oversight before, right? So who really decides how to control the traffic? Like if you read literature, they usually talk about these metrics that, you know, they kind of seem to make sense, right? Like we want to improve average travel times, we want to improve throughputs, these kind of things. But like traffic is really complex. There's a lot of things you could improve. You could also think about sustainability explicitly. You could think about noise. You could think, as they did in the Netherlands, for example, of like promoting different modalities, right? So you want to make traffic good for cyclists, but not so great for vehicles. In some places in the Netherlands, I'm pretty sure they make it difficult for the drivers on purpose. So that's a very, you know, different kind of approach that you might expect. And so really with all these different approaches, should it really be the engineers who design these methods who ultimately decide what is being optimized, what is being followed? And I believe it's not really the case. So I wanted to kind of democratize, have a system that is a bit more democratic. And so, and this democratization will actually allow for multiple objectives to be pursued, right? So not necessarily just one kind of metric that we're trying to optimize, but you know, we can, using this, we can account for many different preferences. And so how do we do it? So classical machine learning, price light, but also the guided light method that we proposed, they just have this reward that they're trying to estimate. And then we're maximizing this reward. And in this case, we've used pressure. And this is this kind of funny measure, which is quite liked in the traffic science because there are certain guarantees. You know, someone established under certain conditions, certain proofs and guarantees on how optimizing pressure locally will affect the system globally. It's generally quite hard to kind of draw this conclusion. So everybody likes pressure because there are these guarantees, of course, under conditions which are often also not met, but it works fairly well. And it's basically the imbalance between the number of vehicles on the incoming approaches and the outgoing ones. So you can imagine like the intersections just trying to balance out how many cars are waiting to go in and how many cars are kind of going out and then waiting on the next intersection, right? So that we don't push too many to one side because that would usually lead to congestion. And so what we propose is a bit different. So we propose to have a few models, a few neural networks, each optimizing, estimating a different reward, right? So that gives us a notion what to do to get this reward optimized. And then we want to bring in votes. So that could be drivers, like I say here. That could also be people living next to the intersection, basically like stakeholders, right? People who are affected by how this operates. And then they are allowed to vote on what kind of rewards they care about, right? So you could imagine one reward being about optimizing, let's say, minimizing waiting time. So we're always in a rush. And then at this intersection, you really don't want to wait too long. So you're always voting, let's minimize wait times. But then maybe someone living next to this intersection is like, well, I'm actually not driving there at all. But I really don't like when it's a lot of exhaust fumes next to my house. So I'd rather optimize sustainability. And then so let's see what happens in that case. And so let's say this may be a bit complex, but we'll get through it. So here we're going to be interested in these two measures, the wait times and the stops. And I use the stops as a proxy for kind of a sustainability metric. Of course, you can nowadays also directly measure the air quality around the intersection, but generally we know that most exhaust is produced when the vehicle accelerates or decelerates. So basically, when it comes to a full stop, that affects sustainability negatively. And here I'm showing results. I'm also showing speed for sort of like sanity check. You know, if the speed got very low, it's even if we have very high, very good results in one of the other metrics, if the speed is very low, that might suggest something is going wrong. And here it's a simple scenario, just one intersection. And we're having going for this intersection, the voting population is split 50-50. So half of it wants to optimize the number of stops, minimize them. So they're sort of caring about sustainability, and half of them want to minimize the wait time. So they're a bit more selfish. And so let's maybe start with the orange triangle. So that's the number of stops. And so to your left, you can see that we almost get to 0 stops. That's pretty good. Like we almost get the global minimum, really. Nobody has to stop. But then the wait times are actually quite high somehow. And then conversely, for the wait times, we actually do get to the global minimum, the 0 wait times, but they have to stop all the time. So they're like kind of like stopping and going, like terrible for any kind of sustainability. Now, when we use our system, and this is both these purple and blue triangles, and the difference between them is how we aggregate the votes. So that actually quite affects our system. And the better way, it seems, to aggregate votes is to use proportional aggregation instead of majority voting. And so perhaps we can just focus on the blue triangle. And here we can see with the population split 50-50, we get quite good in terms of number of stops, not really global minimum, quite good on wait times, not really global minimum, but it's good on both, right? So you kind of get to satisfy both groups. And actually the speed, I think, is quite high, quite the highest, it seems. So, the system works quite well. But then someone could say, well, okay, but so, we could just vote once and then everybody would know, if it's 50-50, and then we could just train a model to satisfy this sort of split of have the people want wait times and have the people want stops to be optimized. And so we also compare our method to a machine learning agent, which is trained on a combination of these two rewards. And we use linear combination and Cobb-Douglas combination. And what we see here, surprisingly, quite surprisingly perhaps, these combinations are not really able to express the changing preferences in a good enough way. Because when we use Cobb-Doug, it optimizes actually wait times. And when we use the linear combination, actually optimizes the stops. And so then again, our method is kind of superior because it's able to satisfy both of these objectives. All right, so I think that brings us to conclusions. We pose these two questions. We're interested to see how machine learning compares to the already existing adaptive methods because of the kind of, this thing was missing from the literature, it seems. And what we saw at first is that this kind of out-of-the-box machine learning solutions, they actually struggle to outperform this analytic method, which is, I think, published in 2008. So that's a bit, disconcerting, I'd say. But then if we play around with it a bit, if we use this analytic insight for exploration, for example, we can outperform both machine learning and adaptive methods. So, combining the two, this kind of hybrid solution seems to work best. And then we propose certain other improvements for machine learning. And so that would be the length invariant state design, the value of pre-training on simpler scenarios that have more meaningful information. And then, we show that we can also kind of leverage machine learning, these different models of rewards to get multiple objectives satisfied and also have some sort of democratic oversight over the system. Okay, thank you, and be very happy to take questions.